we often consider situations in which our data, we're going to call it, and I'm going to refer to it throughout this presentation, the set of xn, n going from 0 to infinity, are independent, identically distributed, which we say IID, samples from a population. However, in many situations, it may be unrealistic to assume that the xi are independent or that they have the same distribution. For instance, suppose that xi measures the value of the stock on day I. Then it is not reasonable to assume that xi minus 1 and xi are independent. For example, if a stock was highly valuable yesterday, then it will probably also continue to be highly valuable today. Additionally, in any realistic model, the distribution of the stock price should change over time as well. For instance, it might make sense to assume that the volatility or variability of the stock will increase with its value. So here in my example, this is the Boeing stock price for the month of May. And you can see, it's kind of staying within a range. It's not like, it's still kind of within, $100 and something under 200, right? So that's what I mean. So why would we want to make the assumption that the data is independent and identically distributed? Guesses? Suggestions?
It makes it easy to deal with stuff, because a lot of random samples have properties that are useful.
Exactly. So, okay, the assumption that our data is IID is extremely useful, as it allows us to derive limit theorems, such as the law of large numbers and the central limit theorem. Okay? If we make too few assumptions about the structure of our data, then analogous results might fail to hold, and so we might not be able to say anything useful about xn, our example data from, our first slide. So accordingly, it is natural to ask what a reasonable alternative to the IID assumption might be. It turns out that in many settings, a useful balance is given by the assumption that the future, given the present, is independent of the past. In other words, we assume that as long as we know what happens today, then knowing what happened on past days doesn't give us any additional information about what will happen in the future. Okay. So mathematically, I have here, for any event A, subset in the real domain, the probability of xn plus 1 occurring as an element of A, or event A, given x1, x2, so on and so forth, xn, is equal to the probability of xn plus 1 being an element of the event A, given xn. So note that it's just saying, hey, the most recent event, xn, is kind of what we're looking at to get the probability. It's going to be the same as if we account for if we know the previous steps. So that brings us to a formal introduction to Markov chains. So, I think I'm going to give you a moment to soak this in rather than reading it out to you in the interest of saving some time. And I'll also mention that this presentation will focus on processes that have a discrete state space. I might call this time homogeneous going forward. And in this setting, this property is formulated as this following definition here. It is convenient to consider time homogeneous Markov chains for many reasons. For example, if we hope to extract some statistical information from a system, it doesn't matter when we start observing it. More practically, their analysis is much more straightforward over processes in the continuous space. So the following example illustrates how one might use Markov chains to model physical systems such as weather. All right? So each day in my example, if it is sunny, there's going to be a 95% chance that it'll be sunny the next day, and a 3% chance it'll be cloudy the next day, and a 2% chance it'll be rainy the next day. Okay. Note that if given a day, let's call the given day today, if today is sunny, then these are going to be the probabilities for my weather tomorrow. Okay, notice that it's going to be, for 100% positive, that it's going to be either sunny, cloudy, or rainy. All of those probabilities add up to 100%. Okay. But suppose today was cloudy, all right? Then there's an 80% chance that tomorrow is sunny, 15% chance that tomorrow is cloudy, and 5% chance tomorrow is rainy. And finally, if today is rainy, then there's gonna be a 75% chance that the next day is sunny, a 15% chance that the next day will be cloudy, and 10% chance that tomorrow is gonna be rainy, okay? So we can model the system as a Markov chain. So its state space is the set of SCR, which stands for sunny, cloudy, and rainy here. And its transition matrix is given by this following P matrix here. And you can see that I have my probabilities. Note that by row, so this top row represents all of the probabilities for weather tomorrow, given that today's sunny. All right, so that's going to represent all of the probabilities for that. The middle row I have here is the probabilities for tomorrow's weather, given today being cloudy, and the bottom row represents the probabilities for tomorrow's weather, given today is rainy. So the question I want to ask here, if it is sunny today, what is the probability it will be sunny in 2 days? Oh. Okay, I can see we're not going to do this off the top of our heads, so let's look at the next slide to find out what's going to happen. Ooh, okay. So let's let xn denote the weather of the nth day from today. So we're given that today, that's 0 days from today, so we'll call it x naught. Okay, x0, x sub 0, x naught. So we're given that today is sunny. Then Markov's property ensures that the probability of 2 days from today being sunny, given today is sunny, all right, is equal to, I'm gonna go through this now, the probability of 2 days from today being sunny, given that today is sunny and tomorrow is sunny, times the probability of tomorrow being sunny, given today is sunny, plus the probability of 2 days from today being sunny, given that today is sunny and tomorrow is cloudy, times the probability of tomorrow being cloudy, given today is sunny, plus the probability of today's from today being sunny, given today is sunny and tomorrow is rainy, times the probability that tomorrow is rainy, given today is sunny. Wow, okay, that's a lot of stuff to say. But we're gonna use that property to try and make it a little bit more simpler. So note that in the first part of these equations, right here, okay, we're talking about, we can restate it to reflect that Markov property, that if we know the weather tomorrow, then the weather today doesn't really affect the probability of sunshine 2 days from now. We can write this as shown in the second equality, okay, that's that second chunk right here, that all of the above was equal to the probability of 2 days from today being sunny, given tomorrow is sunny, times the probability of tomorrow being sunny, given today is sunny, plus the probability of 2 days from today being sunny, given tomorrow is cloudy, times the probability of, well, tomorrow being cloudy, given today is sunny. And then here, finally, we have plus the probability of 2 days from today being sunny, given tomorrow is rainy, times the probability of tomorrow being rainy, given today is sunny. So you can see that what we end up with here is we have this sum of the probability of the weather going from 2 state spaces, sunny to sunny, times the weather going 2 state spaces, sunny to sunny, and that represents, you know, sunny today going to sunny tomorrow, times the probability of sunny tomorrow going to sunny 2 days after, right? And so on and so forth for the rest of it, and you can see that. Well, we have the probabilities from our P matrix from the previous slide. So we can plug those probabilities right here. We can calculate that. And so, we find out that the probability that 2 days from today it will be sunny, given, well, today is sunny, is about 94%. Questions?